We're going to have a very interesting sessions. So we're going to start straight away with the first speaker, which is Willem Mulder, talking about treating disease by focusing on innate immune system.
Okay, I'm not sure. Okay, it's working. Oh, okay. That was me. Yeah, just my background. I've been at Mount Sinai from 2006 through 2020. The first half of the talk is about the developments that at Mount Sinai we're trying to translate to the clinic. In 2021, I migrated back to the Netherlands, and then I give a little bit of a snippet what we're building, to facilitate translation of nanomedicine. We're focusing on immune-mediated diseases. Obviously, everyone has heard about CAR-T and checkpoint blockade therapy. But we're going more upstream, and we're focusing on innate immunity. Our innate immune system, our entire immune system, originates in the bone marrow, so we're focusing on the bone marrow. I won't go into the details too much about what it is we do exactly and what let's say, the molecular processes are. But it's very important to realize that when we focus on the bone marrow, not on a specific disease, and we try to take control of immune responses in let's say, conditions where there's dysregulated immune responses. So what does that look like? It could be something like this. So we develop these nanomedicines. They accumulate in the bone marrow. And then on the one hand, you have conditions that are characterized by excessive immunity, autoimmune disorders, cardiovascular disease, organ transplantation is something that we're very keen on. And on the other hand, you have conditions that are more, where the dysregulation is more in the space, in the realm of immunosuppression. We now know that, for example, in cancer, immunosuppression actually originates from the bone marrow. That's where it's orchestrated. And so many people focus on the tumor microenvironment, but there's actually communication between the tumor and bone marrow progenitor cells. And that's something that we've shown in mice and now also in human subjects. Okay, so what is our nanomedicine platform? We plagiarize nature, and we focus on lipoproteins. And lipoproteins are the transporter, the nano-delivery vehicles of our body. They transport fatty molecules throughout our body, and they're essentially composites of apolipoprotein and fatty molecules, and they have all kinds of interactions with immune cells. So it makes a very attractive concept. If we focus a little bit more on the morphology of a lipoprotein, it really resembles these lipid nanoparticles because you have something hydrophobic on the inside, typically containing triglycerides, cholesterol esters. Then there's phospholipids and cholesterol incorporated. And then you have something that stabilizes it. And different from lipid nanoparticle technology, we have proteins that stabilize these particles. They integrate in these lipid aggregates. And we primarily focus on apolipoprotein A1. And so using natural building blocks, apolipoprotein A1 and all kinds of different lipids, phospholipids, triglycerides, cholesterol, and we can create these libraries of what we refer to as nanobiologics. And nanoparticles that contain a protein, hence a nanobiologic, that have, because of the integration of ApoA1, have inherent affinity for myeloid cells and their progenitor cells in the bone marrow. Now, so we very extensively evaluated this concept. Just a few highlights in immuno-oncology. We do it in organ transplantation very effectively. We're already at the level that we're doing this academically in non-human primates and in the space of cardiovascular disease and organ inflammation. Okay, so this is the work that we've done academically in the United States at Mount Sinai. And then in 2019, we spun off Train Therapeutics Discovery. I serve as the company's CSO. This is a little bit projection. I love windsurfing. But essentially, try to regulate these immune responses, take advantage of these immune responses, although they can be very dangerous. That's kind of like what we're trying to convey here. Scientific founders, where I was the main initiator. And we started back in 2019. I was essentially running a virtual company, but now we've grown to, it's almost not a startup, it's more of a scale-up. I think some of you may have seen the lectures from Christiane, so she's very intimately involved in helping us with chemistry, manufacturing, and control. And she has her own team. I focus more on the science and let's say long-term planning, strategic planning. And Joost Keijs has been instrumental in making this company a reality. Advisory board, we have an immuno-oncology team, a Nobel Prize winner, Jim Allison, and his wife, Pam Sharma. Lex Egermond, they actually met for the first time at Cleanam due to TON. And then this is at the side of immuno-oncology. Then for organ inflammation, we have Mihai Netea, who is, let's say, my partner in everything we do. He's the immunology wizard. We then develop, based on these concepts, we develop new technologies. And colleagues from Radboud and Greece. I'll just show you one thing. We started focusing now with the company, or at least, no, that's not focusing. We started prioritizing the immuno-oncology program. That's the board of directors that decides that. And so this is the concept that we're pursuing, and we've shown preclinically this to work really well, but also in an ex vivo setting. So intravenously administered nanobiologic. This is a nanobiologic on which peptidoglycan derivatives are templated. So this is what you could consider a nanomicrobe. It is essentially a piece of bacterial wall that is very effectively inducing an immune response. And this stuff accumulates in the bone marrow and therefore has direct interaction with immune cells in the bone marrow, but also with stem and progenitor cells. And that causes a type of myelopoiesis that, from a distance, changes the tumor microenvironment from immunosuppressive to more of an anti-tumor microenvironment. So we can change the tumor microenvironment by targeting the bone marrow. Now, we're located in the Netherlands now. I moved to the Netherlands. I live in this city called Eindhoven. That's also where I have one piece of my academic lab, and then the other part of the academic lab is in Nijmegen. And squeezed in between is a town called Os, which is known for sausages and the Socialist Party. But it's also known for a pharmaceutical company called Organon. And they were behind, for example, insulin. That was actually the reason Organon was founded. So this is a bioscience park with a very rich history of drug development. We're doubling in size every year now, and so we're also quadrupled in size with our lab space. And I'm very excited to share this with you. We did our dose range finding batch in-house, and this was back in July. Currently, we're executing dose range finding studies in rats and non-human primates. Next year, there will be a very extensive toxicology program to plan to be in the clinic in 2025, starting our phase 1 study. So we've prioritized our immuno-oncology program, but we have two other programs, organ transplantation program, which also has been thus far mostly an academic endeavor, and an inflammatory diseases program. These are in the preclinical stage, still in development, and so we've prioritized this. Okay, so spending almost 15 years in the US, and then building that company. So when I was returning to the Netherlands, because over the course of 2020, a lot has changed for a lot of us. And so I decided to then rebuild a research program that also includes translation in the Netherlands. Now, there's a little different environment in the Netherlands. So I need engineering and I need like a medical school. And so we have the Radboud University Medical Center and then the Eindhoven University of Technology. Here we have a team of, let's say, about 16 people working on the technologies, and then we have a team at Radboud UMC, about 10 people working on evaluating these technologies in preclinical models and ex vivo models. So this is the new group. I want to also acknowledge Johanna. She was my lab manager in New York, and she joined me. She's tiny, so there was easy travel. And she's my secret weapon, and so not so secret anymore. I've been saying this many times. But to build that research operation, I've been very lucky to recruit very good people. Evelina Kluse I've been working with for a long time. Thijs Beltman is a former PhD student. And then actually Tom connected me to Roy van der Meel in 2018. And so I started working with him in 2019 on a new platform technology for RNA delivery. Because what do we want to accomplish? We actually want to be able to control this process, the hematopoiesis, at the level of stem and progenitor cells, but also at the level of mature myeloid cells and mature lymphocytes. So we wanted to build delivery technology that's very specific and is tailored designed towards immune cells. Yeah, so this is Roy. I'm going to present the study that he's been working on for almost 5 years now. And this is really his work. And we started working together back in 2019. He's a prolific speaker. But we started working on, let's say, that lipoprotein trafficking through the body for RNA delivery. So we have the RNA component. We have to make that hydrophobic. It integrates apolipoprotein A1. We typically also maybe mix in triglycerides as kind of like a lubricant for these formulations, phospholipids, cholesterol. And so we first built a prototype. So Roy and I had the idea, like, okay, let's make this work, but you don't really know where to start. So we built a prototype where you can see, these things are spherical, pretty monodisperse. ApoA1 is integrated in the surface of these particles, as we show with essentially staining with gold nanoparticles in an antibody. We have better silencing features than, let's say, standard lipid nanoparticles. We then radiolabeled the siRNA, which is in this case a therapeutic payload, formulated that, and then we can see how free siRNA behaves compared to LNP-formulated siRNA and a prototype AMP. That was just the start, and then we had a very extensive study where we built a library, where we changed all kinds of parameters. In the sake of time, I won't go into too much details, but it looks something like this. And so we built that library. Initially, or in total, we formulated more than 400 different AMPs, and then we've done some quality checks. Do they aggregate? Are they stable, etc.? So in yellow highlight, you see all the ones that pass the quality control. And very excited that we have the cryo-EM of all the formulations. Evelina Kluza has done a tremendous amount of work. We look at other parameters like aggregation, shelf life, and obviously gene silencing in vitro. And from this library, we selected 8 AMPs that are representative of the diversity within this library, and then screened against LAMP1, because that's something that's expressed on the cell surface and it can be detected by flow cytometry. Now, different AMPs, and we see pretty interesting behavior. So we can silence genes in hematopoietic stem cells with a few of these formulations. And we're very excited about that because that opens up a lot of opportunities for the regulation of immune response, but also for regular therapeutics. So then we have an overview here. We have these different AMPs. And so we go more to the stem cells. These are myeloid progenitor cells. And you see that this AMP18 has pretty broad silencing features. And so we thought, like, okay, let's take a safe bet, because, for example, this one is mostly myeloid progenitor cells. And so we further analyzed this AMP18. We looked at the reproducibility of this batch. Yeah, this is a different identifier, but it's this batch. So you can see that 6 different batches. They all look identical on cryo-EM. Yeah, and so now we have a platform that essentially has the capability to target hematopoiesis and all the immune cells involved in our host defense. But we're pretty good at targeting this part, including hematopoietic stem and progenitor cells. Lymphocytes is more tricky. And we've seen lectures earlier today where we see, okay, then how do you target, for example, lipid nanoparticle technology? For this AMP technology, we devised a very elegant strategy. And that's we create fusion proteins between apolipoprotein A1 and targeting moieties. And so it's more nuanced. It's not like you have a PEG and then you have to do conjugation chemistry. No, we recombinantly produce proteins that have because of the addition of targeting moieties. In this case, it's a nanobody specific to CD8. CD8 is a marker for cytotoxic T cells, and we get very nice specificity. And I want to show you, I'm going to show you data. These are among the best data that have been produced in my lab. And just to show you how well this targeting works. So bear with me, okay, that was a cartoon, but it's about this. So here you see very efficient CD8 targeting in the spleen, in the bone marrow, in blood, in lymph nodes. But it's not only targeting, what we also see is detargeting. So with the fusion protein AMPs, you see reduced uptake in the off-target cells, in myeloid cells and CD4 cells. And so these are very, in our opinion, very strong data for targeting this AMP platform to other types of cells. This obviously does not only apply to lymphocytes, you can also focus on myeloid cells if you want to be more specific and use this type of technology. Okay, so the plan now is we have the Eindhoven University of Technology and the Radboud University Medical Center with off squeezed in between. So we built a biotech incubator called BioTrip that owns all the IP of all the stuff that I've shown in this lecture. And it's something that we're developing now and we're trying to use as a platform to spin out new startup companies. And we have this RNA platform, we have the targeting technology. 6 months or so ago, we published about immunoregulatory AMPs. These are fusions between ApoA1 and cytokines. And we're working on these concepts for local immunoregulation. We have a big IP portfolio that we're now working on, and we're working on, with investors to start or to essentially establish the first company. Yeah, I think I'm on time. There's a lot of people that are involved in this, and I'd like to thank you for your attention.